One smart way of counting the number of desired objects is to count the number of non-desired objects and subtract that from the total number of objects. This type of counting is called complementary counting. So let's say we had a can of paint. It has squirrely paint and dotted paint. Instead of directly measuring the amount of squirrely paint it has, we can measure the amount of dotted paint in this can and subtract that from the total amount of paint in this can, and that will give us the amount of squirrely paint. Let's try one example. How many of the first 1,000 integers are not multiples of 11? So how many of the first 1,000 integers are not divisible of 11? Instead of counting every single integer that's not a multiple of 11, let's count the number of integers that are. So 1,000 divided by 11 gives us 90.9. Since we can't have 90.9th of a number, we say that there are 90 integers. 90 integers that are divisible by 11, that are smaller than 1,000. Since we have 1,000 integers in total, and 90 of them are divisible by 11, and all numbers are either divisible by 11 or they're not, that means 100 minus the number that are divisible by 11, which is 910. 910 would be the number of integers that are not divisible by 11. So complementary counting is very powerful. It's fast too. Let's solve another problem using complementary counting. There are 4 boys and 4 girls sitting on an 8-person bench. How many ways can the 4 boys and 4 girls be arranged such that each boy does not sit next to a girl? In other ways, how many such rearrangements are there if BG, BG, where B and G represent boys and girls respectively, or GB, 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 GB does not exist? One way to solve this problem is by listing every possible boy-girl arrangement. For example, one of them would be all boys followed by all girls. Or we can have boy, girl, 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 boy, boy. And we can list all of these arrangements, and that will give us a total number of arrangements for which a boy does not sit next to a girl. But let's use complementary counting because it's going to be faster. How many ways, how many total arrangements of boys and girls are there on this bench? Well, we can have 1 of 8 people in the first seat. We can have 7 in the second, 6 in the third, all the way to 2 and 1. So we have 8 factorial minus the total number of ways where a boy does sit next to a girl, and that's 2. So our answer would be 8 factorial minus 2, which is the total number of ways a boy does not sit next to a girl on this bench. Let's try one more problem. A coin is tossed 5 times. Such 5 times is known as a trial. How many trials contain at least 2 heads? One example of a trial that contains at least 2 heads would be tail, tail, head, head, head. Here we're going to assume that permutation is being used, so order matters. Another example of a trial would be head, tail, tail. We can solve this problem by counting the total number of trials that have 2 heads, the total number of trials that have 3 heads, the total number that have 4, and the total number that have 5. But let's use complementary counting. How many total trials are there? Since each coin flip can either be head or tail, and we have 5 coin flips in total, we use the fundamental counting principle to arrive at 2 to the power of 5 equals 32 total trials. How many trials has less than 2 heads? AKA, how many trials has exactly 0 heads? Well, that would be all tails, which is one possibility. How many trials has exactly 1 head? So in this case, the head can be in the first position, or it can be in the second position, or third, or fourth, or fifth, for a total of 5 ways, 5 trials that have 1 head. So the total number of trials that have at least 2 heads is equal to the total number of trials minus the number of trials that have exactly 1 head, that have exactly 0 head, and 1 head, which gives us a total of 26 trials. Thank you for watching.